Hello everyone. This is Dr. M. Venkateswara, Department of EC, Pace Institute of Technology and Sciences at Autonomous. So today I am going to teach about microwave and radar engineering. This subject will be present in third year, second semester EC department, and this subject deals about the basics of microwave, the microwave devices, the microwave tubes, as well as radars, different types of radars and their application in space communication, etc. So in this session, I would like to tell about the microwave, basic microwave devices, types of microwave tubes, as well as the real-time applications of microwave. Coming to the microwave engineering, the word microwave stands for micro level wave application. Generally, if you take any amplitude ranges, that amplitude will be peak to peak is up to some nanoseconds. But whereas when the wavelength is very small, the wave should be in very small area. So if you take that wave into consideration, the microwave will be propagated in gigahertz range. So coming to this, a student will be get benefited about this course by knowing the microwave bands which will be used for our day-to-day scenario, as well as the bands which we will be used for the cellular communications, satellite communications, as well as the real-time applications. And also this particular course has an interaction with the active and passive devices, microwave devices. So those devices, those bands, etc., we will be seeing in this session. So and also this is having a understanding about the microwave bench setup and its measurements. So coming to the learning outcomes, a student will be able to get and understand the microwave solid state devices, microwave tubes, as well as the characteristics of microwaves. So coming to this session, today I will be telling about the introduction of microwave as well as microwave tubes. So in this session, I want to cover about introduction, microwave spectrum and its bands and its applications, as well as a small introduction to the rectangular waveguides, which are the basic microwave devices, as well as microwave tubes. So coming to the bands, so these are the microwave bands. So the word microwave, which tends to say that it works in the gigahertz range. So this gigahertz ranges frequencies will be seen in the day-to-day scenario. We will be using our Bluetooth, we will be using our Wi-Fi, we will be using our WiMAX, everything which is using the microwave devices. So if you see here, the microwave bands, they are desperately divided into so many types: L band, S band, C band, X band, Ku band, K band, Ka band, etc. like that. All these bands have some specific ranges. These bands works for certain applications. Suppose let us consider L band, 1 to 2 gigahertz. So we prominently know about GPS antenna, global positioning system, which works at 1.5 gigahertz. So in L band, we will be using the GPS. Like that, 2 to 4 S band, the day-to-day scenario applications such as Wi-Fi, WiMAX, as well as Bluetooth, LTE, 4G and 5G communications, those bands will be at S band. Similarly, like that, every band has its own applications. Coming to C band, X band, Ku band, K band and K band. So what we need to learn from this particular bands is, we need to learn the devices, where it is working and how it is working and on what basis it is working. So if you consider here, these microwave bands will be up to K band. So grammatically we can say up to 40 gigahertz due to the usage of the scenario, day-to-day scenario. So possibly the microwave band can extend up to 300 gigahertz until sub-millimeter wave applications. So which is also comes under terahertz. So not only that, this particular frequency levels will be estimated in terms of low frequency, high frequency, medium frequency, or else ultra high frequency. If you consider here, 30 Hz is the least frequency, whereas the visible light travels at 100,000 terahertz. So if you consider these particular rays, low frequency, very low frequency, high frequency, medium frequency, very high frequency, ultra high frequency, and super high frequency. So what these particular ranges will say is how the light travels within these frequency bands. So we will get a clear idea if you know our bands, if you know our applications, if you know our wavelengths, if you know how it is working in this. So we can know the introduction part of this microwave bands. Similarly, if you consider the gigahertz range, terahertz range, or kilohertz range, all these things. See how it is denoted with the symbols you can see here in this table. So the gigahertz which we are doing G 10 power 9, the below one megahertz 10 power 6 M, and terahertz 10 power 12 T. So we will be working on gigahertz 10 power 9. So these microwave what we will learn in this course will be in gigahertz range only. So the higher frequency we will be having, the higher frequency of microwaves, it lies in the borders of the infrared and visible light spectrum. This explains why these microwaves have prominent role when compared to the visible light and the ordinary radio waves to transmit the ordinary radio waves, as well as the unique behavior to set the microwave frequency bands. So coming to this, there are some of the applications from 3 Hz to 30 terahertz. So there are so many prominent applications which we will see in the day-to-day scenarios. So if you see here the band designations from 0.3 to 3 terahertz, 0.3 Hz to 3 terahertz, you will be considering this division L band, LS band, S band, C band, X band, KU, K and K band. So mainly the operation of microwave devices mainly comes in this particular region which I have highlighted here, K band, Q band and U, M, E, F bands. So these bands will be working for the scenarios, for the applications, for the defense applications, for the military applications, for radar applications and for satellite communications. So coming to this, these military microwave frequency bands and this propagation where it will be used is in detailed explanation here. So if you see here how it is propagation will be occurred, and with that propagation what is the application we can be taken. So penetration into the earth at the frequency range of 30 to 300 Hz. What will happen? What type of applications we can get? We can get communication with submarines. So for this frequency band, we will be getting communication with submarines. And coming to this very large frequencies, which is ranging from 3 to 30 kilohertz. So what happens here is, it can produce or it can mix up with the surface waves of up to 1000 kilometers. So which can be further useful for the long distance point to point communication. Nowadays point to point communication is playing a vital role for getting the demand and supply of the users. So coming to the next one, which is 30 to 300 kilohertz, what happens here is surface waves and sky waves at night, which will be attenuated by using very high frequencies to produce the waves and to produce the applications and to get the point to point communication with standard frequency broadcast. Let us say the example of FM or AM radios. even it is day or night, we will get the same standard of signal. So that point of contact will be coming from very large frequencies, that is ranging from 30 to 300 kilohertz. So similarly, if we go middle frequency, higher frequency, very high frequency, ultra high frequency and super high frequency, every band has its own advantages. Let if you consider the middle frequency, you will be getting a broadcasting and marine communication. And if you consider the higher frequency, you will get a moderate and long distance communications of all types. So everything will be traveling as like the wave travel in the velocity of light. So this is the propagation characteristics of various applications in the microwave frequencies. So coming to this, I'll have some examples of applications. So these are some of the applications where you can use the microwave devices. First and foremost thing is the telecommunication. So since from a portable phone to 5G usable mobile devices, this done because of the antenna which is working at the microwave frequencies. If you observe here in telecommunication scenario, in a satellite communication scenario, in train to infrastructure interwagon scenario, and all these scenarios, in all these scenarios, the microwave applications will be widely used. So some of the telecommunication applications which I have mentioned here, there are so many things, but due to compact, I am displaying only 2 or 3 applications: intercontinental telephone and TV, spatial communications, which will be communicated from earth to surface or surface to earth, and then telemetric communication link, which will be mainly useful for the railways. So not only this, the main applications for next CVOs, which I am going to the next CVOs, the radars. See, these are the radars. By using radars, we can detect the, we can track, we can observe all the day-to-day scenarios. We can track the weather patterns. We can know the air traffic controls. We can detect the aircrafts which can be attacked in the war fields. So all these things will be done by knowing the, by placing the radars. So these are some of the examples. So this is some radar station at Vizag. I think this is the Kailasgiri hill, and then this is how you will be predicting from the Indian Meteorological Department weather patterns by using the MTI radars, which will be coming in our further units, further course outcomes. So, and this is how ATC, air traffic control, will be displayed here. So this air traffic control will be done here. So it can be controlled by using the radars. Not only this, V2V, V2X, vehicle to vehicle, vehicle to base station. These communications will also depend upon the radar applications. So coming to the commercial applications. In our commercial applications, there are so many equipments which will be using the microwave frequencies. Some of them are microwave ovens, which we will use to increase our range, increase our heat, drying machines, food processing industry, rubber industry. So not only this, it is also useful in electronic warfare. So these microwave devices will be used in different scenarios, different applications, which will be used to get the part done. So one of the prominent thing about microwave is microwave waveguide. These microwave waveguides are the electromagnetic waves along transmission lines and cables, which is used as a metallic tube to transmit the EM waves. So which is greater than 3 GHz is termed as the microwave waveguide component. So this component looks like a hollow metallic tube which is having a uniform cross section for transmitting electromagnetic waves to get some successive reflections. So if typically a waveguide is a box which is consisting of 6 types, 6 sides: front, bottom, side and left. So there are some waves, transverse electric waves, transverse magnetic waves, and frequency ranges and their inner surfaces, which will be used for the waveguides to propagate. Again, these waveguides are again divided into 2 types. One is rectangular waveguide, another one is circular waveguide. First and foremost thing, the wave traveling in a waveguide has a phase velocity, and a wave which is having reached to the destination, it will be having the load impedance. So the initial velocity is called phase velocity. The initial velocity which is observed is at load impedance. So the irregularity in a waveguide, the irregularity of a waveguide can be seen in this transmission line. So these are some of the types of waveguide. One is a rectangular waveguide which looks like a rectangular structure, and another one is circular waveguide which is having circular in structure. So these two uses Cartesian coordinate system and cylindrical coordinate system. Okay. So coming to the next, so there is comparison between the waveguide and a transmission line. Definitely a transmission line is a device which will be used to transmit a signal from one place to another place, but here the waveguide is a type of device which will be storing the transmission, and at particular frequency it will operate that storage. So not only this waveguide has a one conductor as well as the whole body of this acts as a reflector. If you compare here how the waves are transmitted from one wall to another wall, the wave will be transmitted, and from that wall to the wave will be shifted to another phase. It touches the return wall and then it goes on like this. So you can see the velocity here. So a typical example of how reflection and standing waves propagate in a rectangular waveguide. How we will be giving the excitation. This black symbol which I have indicated is the excitation given here. Okay, and then these are the shorting planes where you can insert the ports. These are the reflections which you can take. So not only this, there are some other feeding techniques. There are some other types of waveguides. These are some circular waveguides, single rigid, and this is a double rigid. You can see how divided it is. These are all types of waveguides. So these waveguides are one of the solid state devices which will be used in the day-to-day scenarios. Okay. So now coming in deep about waveguide patterns. So these waveguide patterns, how it is, there are two modes in the waveguides: transverse electric modes and transverse magnetic modes. So these modes will be used to define the dominancy of the current vectors, electric field vectors, as well as the reflection, how much it is reflecting, how much it is transmitting. Those vector information will be known by the TE and TM modes. If you consider a wave or a surface which acts as a conductor, the electric field cannot have a component parallel to it. If the surface is parallel to the electric field, the wave cannot be propagated, and then the electric field must always be perpendicular to the surface at a conductor, cannot have a component parallel to the surface. So what happens here is the waves which are traveling in the waveguide will be interfering with the conducting walls which are made up of copper and pure metals, aluminum, copper, like this. So if you see this equations here, what happens here is how much the electric field strength will be obtained by using the wall of a waveguide. You can see from this equation. So if you see here, both the two walls, electric fields will be having perfect electric condition type of things, and a box consisting of 6 planes, whereas 2 will be coated with perfect electric conductor, 2 will be coated with perfect magnetic conductor, and the remaining two things will be ported for a source out. So this particular statement will justify that we will be inserting electric field distributions here, and remaining 2 we will be inserting magnetic field distributions, and then remaining the walls will be used to give the port. So n cap dot ds is equal to rho s, which will assume that it is a perfect conductor on the walls of this waveguide, and similarly by using the Maxwell's equations and demonstrating these equations, we will be knowing the waveguide and its frequency levels. So we will observe how the patterns in the waveguide will be done. So these patterns will be done. So sorry. So here TE modes and TM modes, we can see how the waves will be patterned. The E field is parallelly moving. The same field, the perpendicular way is H field. You can observe in this pattern. Similarly, if you immerse into this E field and H field composition, E field like a feather, it will be moving here and there, and H field will be a wave happening here. So in H field, the wave disturb the surrounding area. In E field, the wave consequently carrying the whole wave. So not only this, coming to this wave propagations. So this is how emergently this wave will be traveling in the waveguide. A rectangular waveguide is a typically box type of structure which is having two conducting walls, perfect electric conductor, which is made up of copper and aluminum, and then its sides will be closed with the ports. You can see here, one phase will be traveling downwards, another phase will be traveling upwards. If here the phase is 90 degrees, here the phase will be 180 degrees. Like that it will be moving, and there is a one good statement which I have highlighted here, these three statements, the TM modes, the TE modes, what is M indicates in the mode and where you can highlight these things. So here TE10 is the dominant mode, the first mode is the dominant mode, that is the thing we need to observe, and in the dominant mode what we can see is the highest cutoff wavelength where you can see the dominant mode. So this statement indicates the dominant mode, and the pictorial representation of that dominant mode proofs you can see here how the wave patterns have been. So these patterns has been taken from the textbook. So what happens here is a current distribution, a electric field vector will be moving here and there, whereas the magnetic field vectors, what it will do is it will disturb the scenario. So if you observe here, the magnetic field will disturb the scenario where the current vectors will be moving from positive to negative, negative to positive to neutral. So you can observe here. So these are some of the patterns, and there are some of the important things. Guided wavelength. So the wavelength which is defined to have a phase shift of 2 pi, that is 360 degrees. Any wave should have a phase shift of 2 pi. It should be up to having a polar plot 360 degrees. What happens here is the wavelength will be having some components, some reflections, some outdoor mutual interactions to that waveguide, considering the x-axis, y-axis and z-axis. So the wave will be traveling like this, electric wave. The magnetic wave will be traveling like this. So by using guided wavelength, we will be knowing the patterns of this waveguide. So this equation, lambda g is equal to lambda naught by root over 1 minus lambda naught by lambda c whole square. By using this equation, we can know any cross sectional area of a waveguide. So this is about a rectangular waveguide, circular waveguide, and its cutoff frequencies and its TE TM modes, how it is propagated, and the dominant mode in the rectangular as well as circular waveguides. Now we will be learning about microwave tubes. See, microwave tubes are the stationary things which will be used for different scenarios. Generally, the conventional tubes has some problems. The conventional tubes cannot work in the gigahertz range. It has inter-electrode capacitance. It has low transmit time effect, gain bandwidth limitations. There are some RF losses. There are some radiation losses, etc. But what happens in the microwave tubes is it has designed to overcome the principal limitations of the conventional tubes, such as the electrode traveling to millimeter oscillations, the electric field distributions, and it won't work at gigahertz frequencies. Those limitations will be overdone by the microwave tubes. Similarly, there are different types of microwave tubes. There are O-type microwave bands, microwave tubes, as well as M-type microwave tubes. If you observe O-type and M-type, the main distribution of this O-type and M-type. So we can observe here microwave tubes, linear beam devices, cross field devices. So there are two types again in the cross field devices. One is magnetron, another one is CFA. And again in the linear beam devices, there are two types, a resonant cavity and slow wave structures, which are non-resonant structures. In resonant cavity, most used thing is klystron amplifier or reflex klystron. In slow wave structures, there are again two types, forward wave and backward wave. In forward wave, there is helix traveling wave tubes as well as coupled cavity traveling wave tubes. In backward wave, there are two types, BWA, backward wave amplifier, and backward wave oscillator. So these are the different types of tubes which are replaced the conventional tubes to helpful in the communication scenarios. So not only this, if you go in detail about classifications, about O types, so same thing you can see here, O types, the cross field tubes which will be used to resonate, the M types. So these M types again two types, resonant and non-resonant, as well as master effect. So in resonant, the major thing which will be considered is standing wave, recentrant. These all comes under one equipment called magnetron. The resonant mode, the standing wave mode, and reentrant, and all these things comes under one device called magnetron. Coming to the non-resonant case, there are two types again. For non-resonant cases, we will be using forward wave and backward wave. So for forward wave, reentrant and non-reentrant. For backward wave also same thing, but the only thing is it will be used for forward applications, it will be used for backward applications. So this is third one, master effect, gyrotrons, which will use it in the day-to-day scenarios. So from this, I can conclude that microwave devices, microwave tubes and its classifications will be used for n number of day-to-day scenarios. In this lecture, we will be knowing about microwave applications, microwave tubes, rectangular and circular waveguides, types of microwave tubes, O type and M type, and its applications in day-to-day scenarios. So from this, I am concluding my session. In the later session, I will be explaining about different types of O type structures and M type structures, reflex klystrons, 2 cavity klystrons, 8 cavity magnetrons, etc. So thank you all.